Hey physics people, so we're back again with another problem. This one's pretty calculation based, so there's lots of calculation, lots of numbers that go on with this one. This is actually how the old AP test used to look, but it's good practice. Okay, so here's the scenario, and I'm going to redraw this in a second. So we have a ball coming down, hitting another ball that's flying this distance. And we're asked to calculate all this different stuff. So calculate the speed of both of the balls, one just before, immediately after. So let's go through all of these. So a lot of calculation. So let's start off with this one. So I'll calculate the speed of the 0.66 ball. All right, so oh, all right, let's minimize that. All right, so I'm going to calculate the speed. Wonder if I can, yeah. All right, calculate the speed of the 0.66 ball just before the collision. All right, let's do a quick drawing of this. So we have, this is 1.2 meters height. We have a length here of 0.6, so length equals 0.6. So this is the m is equal to 0.66 mass. It's coming down, it's hitting a marble. That's mass is equal to 0.22. It says it makes an angle of 60 degrees here. So lots of variables here, or lots of data here. And it goes 1.4 meters. All right. So calculating the speed just before the collision. Well, to do this, you might think like, oh, what am I going to use? And it's conservation of energy. So at the very top, we have mgh. It's got all potential. And then right before it comes down here and hits this marble, it has kinetic. So it has 1/2 mv squared. It's the same mass for both of them, so the mass is canceled out, so that's nice. And if I do a little bit of algebra, moving this stuff around, I get V is equal to the square root of 2GH. All right, seems pretty straightforward and simple, but we don't know what H is. We don't know what this height is, so I'm going to do H in blue here. They don't give it to us. They give us this angle and they give us this length, so we need to find H. So I'll come over here and I'll redraw this. Well, I can do it right here. So we have, this is my L of 0.6. This is 60 degrees. And this is my H right here. This is my H. Okay, so, or you can think of it as this is my H. H. All right. And if this ball swings down, the entire length here is L. All right, so see if you can follow this. I'm gonna add an X here, because if I want to find H, I'm gonna have to take this whole L. So to find H, H is gonna equal to L minus X, right? L, if I take L and subtract off X, I get H. All right, so H is equal to L minus X. Well, what is that X? Well, the X is, this is the adjacent side. So L cosine of 60. Cosine of 60 is 1/2, so I have L minus 0.5 L. So that's equal to just half an L, which would be 0.3 meters. Okay, so if I come back up here and I plug this in, I get the square root of 2 times 10 times 0.3. 0.3 times 2 is 0.6 times 10 is equal to the square root of 6, which is equal to approximately 2.4. All right, a little bit of rounding here. So I get 2.4. All right, that is for A. So we got A done. All right, let's go back and do B now. So B, control B. All right. All right, so let's go to a new page. All right. Okay, so now we're calculating the speed of the 0.22 kilogram ball immediately after the collision. All right, so let's think about this. I'm going right after the collision. Well, in this case, what I'm using here, I want to calculate for this 0.22 kilogram ball, what is the velocity? Well, we've done this in our kinematics section. If this distance right here, they said it was 1.4. This height here was 1.2. All right, I can find how far this thing goes just by knowing the height and the horizontal distance. And the way I do that is I know that it's not accelerating in the x direction. So it's going to be this basic equation, delta x over t. Well, I know my delta x is equal to 1.4. But what's my t here? Like, what am I going to plug in there? And I have to use a kinematic equation to figure that out for the time for it to fall. So here, since it's in the y direction, we'll say delta y, v0 in the y direction minus 1 half. The acceleration in the y direction is g, so I get t squared. Well, when this thing falls, the initial velocity in the y direction is 0. So a little bit of manipulation here, and I get t is equal to 2 delta y divided by g all square root. All right, you might say like, hey, what happened to that negative? Well, technically delta y is -2, so they cancel out, which is a good thing because otherwise you would get a negative under the square root, which is an error. Okay, so let's plug in some numbers here. We get square root of 2 times 1.2 over 10, and that is equal to roughly 0.49. All right, so plug this in over here, 0.49. And then when I do that, I get my velocity is 2.9 meters a second. All right, and labels here really matter. It makes it a lot easier. So you can see that this is equal to the, like I'm going to say 0.22, and so that's the velocity of the 0.22, like initially when it hits. Okay, let's go to the next one now. So we got that one. Right now we are on calculate the speed of the 0.66 ball immediately after the collision. All right, I can keep it like that. All right, calculate the speed of the ball. All right, so this one is a momentum problem. So it's conservation momentum if I'm going to solve for the speed of the 0.66 ball. So conservation momentum says my momentum initial is equal to my momentum final. Well, the full momentum initial is the mass of the 0.66 times the velocity of the 0.66. We can call that like for the collision, we'll call that the initial. And here I have the 0.66 ball. v of 0.66 final plus mass of the 0.22 ball, the v of the 0.22 ball final. Okay, so I have to use some of the things that we solved for before. So remember the velocity of the 0.66 ball, that was for in part A, we found that that was 2.4. So here I'm going to do this. So 0.66 is the mass. The very first velocity we found was 2.4. Now we got 0.66 times, this is what we're looking for, 0.66 final. Now we have the 0.22 mass, and this was the second thing we did. We found the velocity of the 0.22 ball, and when we did that, we got 2.9. All right. Okay. So I'd already done the math here, so the answer that you get is 1.4, and the unit meters a second. Okay. Now we are on part D. Okay, so D. This one's pretty straightforward. I'll just do this one right here. So indicate the direction of the motion of the 0.66 ball after the collision. Is it to the left or to the right? Well, this right here is positive, right? So it's positive. If it was negative, it would be in the opposite direction, but it's positive. So it's the same direction that the ball was moving initially. So it's to the right. All right. Okay, so E. Let's do E now. Calculate the height. So another energy one. So calculate the height that the 0.66 ball rises after the collision. So this is just kind of going back, energy, momentum. So to do that, calculate the height using energy again. So we have, let's see, now we have for the starting energy is kinetic. So I'm going to have mass of the 0.66. And then v of the 0.66 squared is equal to m 0.66 g, and h is what I'm solving for. Kind of nice whenever we can cancel something out. Let's do it. And now let's plug things in. So I have 1/2. Well, here, a better thing to do is just rearrange this so that you're isolating the variable you're looking for. So h is equal to v.66 squared, right, over 2. And I would have to divide this g over here. So the 0.66 squared, that was what we found in the previous problem. So that's 1.4 squared over, and we're using 10 for g, so we'll say 20, which would give us uh, 0.1. And the height, we're using meters. Okay, so now let's do the last one. So remember, the last question is usually the trickiest. So let's see if this is tricky. All right, based on your data, is the collision elastic? Yes or no, justify your answer. All right, so for elastic, you have to know that elastic collisions conserve kinetic energy. So this is a lot of calculation. We're just going to have to see if the kinetic energy initial, is it equal to the kinetic energy final? All right, well, the kinetic energy initial, that was the 1/2 m of the 0.66, v of the 0.66, and that's the initial right before the collision, is equal to 1/2 m of the 0.66 v of the 0.66 final squared plus 1/2 m of the 0.22 v of the 0.22 final squared. So we're going to see if all these things are equal. And we can plug in values here. Here again, like remember that if something cancels out, we can cancel them all out. So here I get 0.66, cross it out, times my velocity, 2.4 squared is equal to 0.66, 1.4 squared plus 0.22, 2.9 squared. And when I do all that math out, here I get 3.8, here I get 3.1. So are these things equal? And the answer is no. So it's not equal. So is an elastic collision? And the answer is no. And that's because some energy is wasted. It goes, so it says justify. You could justify showing this, and you can say that that energy goes towards waste heat and sound. So that means that it's not conserved. Okay, that is the video. Hopefully this helped. And yeah, let me know if you have questions.